So what have we done? So we started with basic Lindeberg principles, just the typical central limit theorem with the Lindeberg condition and with the Lindeberg method. We discussed the Stein method. So then we had a kind of a chapter on methods of proving central limit theorems, which are more robust. And then we discussed more general Lindeberg principles, like the idea of stability. So if you want to convert to prove conversion in distribution, and you have one, you want to show that your functional is in the stable of attraction of something, then how can you use Lindeberg by changing to the favorable variables for which you have, which is the center of the universality. And then we discussed this in the case of in the example of multilinear polynomials, which also play a very important role in stochastic heat equations and polymers and stochastic SPDEs and statistical mechanics. So in fact, actually, last time we discussed scaling limits of disordered systems, where we have a statistical mechanics model and we perturb it randomly. And then we express this through what is called high temperature expansion as a set of multilinear polynomials. And then we obtained a scaling limit by basically changing the general randomness to white noise randomness, and then get a limit which is expressed in terms of iterated Wiener integrals, what is called a Wiener chaos expansion. Today, maybe contrary to what kind of I promised to do, last time we said we will maybe discuss maxima of local related fields, but I thought actually it would be a different course. So, and then I thought eventually it's still better to conclude this as a self-contained theme. And then we will now expand, we will now actually go to apply all these techniques that we discussed in order to see how this can be applied in the critical case of the stochastic heat equation. So today's lecture is more going to be related to my seminar talk last Tuesday, but bringing all the ideas together. Things that are going to pop up in this lecture are going to be variance computations. The multilinear polynomials will play still a role. Levy processes of particular kind called the Dickmann subordinator will show up. And then I would like to motivate how it shows up. Then collisions of random walks will come. And I think there are a number of very interesting questions there. Then we will discuss again the idea how to apply Lindeberg principle to sketch the existence of the critical 2D stochastic heat flow. I will do it, I will sketch both our original approach and also the more recent characterization of Chai. Both of them, they use Lindeberg principle. And then we will maybe make some links to local related fields, because the stochastic heat flow is a local related field, and the Gaussian multiplicative chaoses, which are different universalities. And then probably this will come to the end with a number of questions, and then maybe an outlook that we can, we can all think about and discuss together next time I'm back. Okay, so let's look at stochastic heat equations. And let's say polymer models. Okay, I think I discussed this already, but this will be kind of the starting point here. So we have something which is called the partition function. Partition function is a normalization of a Gibbs measure. And this will depend we will have some temperature beta, will depend on some disorder omega. As we very briefly discussed the last time, this is a discrete version of the Feynman-Katz formula, and then we can express this in this following way. So you have a random walk. So what I'm going to write now is in general dimension, but soon we will specialize to dimension 2. So you have a simple nearest neighbor random walk starting from location X. And then after n steps, it goes to Y. So that's what usually X, Y will indicate the starting and the end position of the simple random walk. And then the discrete version of the Feynman-Katz formula, you take the exponential, and then you sum n equal 1 to capital N of beta, omega, n, Sn, minus, we do a normalization so that the expected value of this is equal to 1. So the expected value with respect to disorder. So just to set some notation, so this will denote the law of a simple random walk starting at X. And double probability or double expectation will denote the law of the family of IID random variables on the space-time domain. Okay. So in particular, yes. So lambda of beta, it's the log moment generating function of the random variable at some location, let's say at 0 and 0. And we assume that these are IID random variables. Okay. So then the expected value of this is equal to 1. And if you want the expected value of the partition function is equal to the probability, the random walk going from X to Y in n steps. Okay. So we are interested to understand the scaling limits of this. Is there a way to tune down beta so that we have a non-trivial scaling limit of this? Okay, and if you think of this as a discretization of the stochastic heat equation, this will actually give you a scaling limit or the solution to the singular stochastic heat equation. Okay, let me remind you how we deal with these things. We perform the chaos expansion. So maybe I'm going to write it very quickly. So the way we did this last time is we put the summation. Okay, first of all, let us write this in terms of the local time. So summation n equal 1 to capital N, and summation x in ZD, omega n x times beta minus lambda beta times 1 s little n equals to, maybe I don't want x, I want z, because x is reserved as the starting location. And then we end up at y. Okay. And very quickly, this is really a recap from last time. We take this product, this sum down as a product. Okay, and then we add and multiply, add and subtract 1. So indicate the function s little n equals z minus 1. Okay, so we have the expected value with respect to the simple random walk, which we pin down at the end to be at location X, Y. And then because this takes values 1 and 0, in fact, actually I can bring this down. So this is equal expected value starting from x, product n less or equal to capital N, z in z2, 1 plus e beta omega n z minus lambda beta minus 1, indicator function that s little n equals z. And then I pin down everything at y at time n. Okay. Now, once we have this, so here I would like not to normalize, so I divide by beta and multiply by beta. So, and I call this random variable psi at n z. So this random variable psi will have mean 0, precisely because here we normalize with the log moment generating function. And asymptotically, the variance is going to be 1 as beta goes to 0. Okay. So for all practical purposes, we can assume that is 1. So now once we expand this product, and then we pass the expectation with respect to the random walk inside the big summation, we obtain the chaos expansion. 1 plus summation k greater or equal to 1, beta to the k, summation n1 less than nk less or equal to n, maybe less than n, z1, zk in z2. And then, so what I'm going to be having here, I'm going to have a product psi and I, zi, I equal 1 to k, right? So the k parenthesis where I picked the psi instead of the 1. And then here I will be having the product of the indicator functions, that Sn at Sni is equal to Zi. But then using the Markov property, I can write this as a product, the probability between time Ni minus 1 and Ni, the random walk has jumped from Zi minus 1 to Zi, where I equal 1 to k. Okay. So here, this part was actually the expected value starting from x. Maybe actually here I'm going to put, let me be a bit more precise. I'll put k plus 1 here because I also want to include the last point. So this is 1 Sn1 equals Z1, 1 Sn2 equals Z2, 1 Snk equals Zk, and then at the end, S capital N is equal to Y. Okay, so here we have the conversions that Zk plus 1 is equal to Y, and Z0 is equal to X. Okay, so this is the chaos expansion that I want to analyze and see what kind of limits I can obtain, if I can obtain any kind of limits. So what I was mentioning is, okay, so can we find beta equals beta n going to 0 so that we can have a proper limit of this? So how do we find the beta n? So already we did a computation similar to this in the more general setting, but let's do it more pedestrian, in a more pedestrian way. So how can you guess the beta? So you would like, ideally, maybe it's not always the case, but ideally you would like the variance, to compute the variance, right? So if you would like to show some convergence distribution, maybe the variance will converge. Okay, the flux, because the variance captures the fluctuations. Okay, you can be strange kind of situation where the variance is not good, and then you will have to do more elaborate things. But precisely the variance captures the fluctuation. So you would like to tune the parameters so that the fluctuations stay of order 1. Okay, meaning captured by the variance. So we can check the first term. So just the first term in the chaos expansion, so k equal 1. That will be what? That will be n1 less or equal to capital N, z1 in z2. And then you will be having, yeah, for the moment, for simplicity, let me make a remark, a notation. So if we have one argument, we understand that the endpoint has been summed out. Okay, and the endpoints being summed out would correspond to this constraint going away, right? So this is called the point-to-plane partition function, because if you think, so you have a random walk starting at x, and then here you want to constrain the random walk going at y, but sometimes you would like to look at all possible endpoints. So you would like to go from point to plane. So this is called the point-to-plane partition function when you sum up the endpoints, so you drop the constraint. So let me also look at the point-to-plane for simplicity. Okay. So the point-to-plane term, first order term in the chaos expansion will be the probability at time. Let's also drop the n1 and the z1. At time n going from x to z. Because of translation invariance, this is just, it depends on z minus x, psi and z. And then we would like to compute the variance of this. The xi's are independent. So here you have a sum of independent random variables. So the variance of the sum of independent random variables is the sum of the variances. So this is like beta square summation n less or equal to capital N z in z2 p n square z minus x, right? And of course, because of translation invariance, if you do change of variables, z minus x, when you sum over all the z's, doesn't see the x, so you get beta square n less or equal to capital N z in z2 pn square z. Okay. Let's do one more step here. So what is this? So this is, you have a random walk, let's say starting at 0, going at time n at location z. Okay, this happens with probability p and z. When you square it, it's as if you have, another p and z. Okay, but this is the same using Chapman-Kolmogorov. If you sum over all possible z's, this is as if starting from 0 and returning back to 0 after 2 n steps. So this is beta square summation n less or equal to capital N p 2n of 0. And then we would like to know how this behaves. So now I'll restrict myself to the two-dimensional case. Okay. Should I restrict myself to the two-dimensional case? Maybe let me not restrict yet to the two-dimensional case. So let's look at the asymptotics of P2n. So we can use a local limit theorem. So the local limit theorem would tell you that this is like approximately up to some constant, and then we know the constant 2 pi n to the d half. Okay. Actually, if you are one has to be careful with periodicity. Okay, so here maybe 4 pi, okay? Because P and X is asymptotically going like the heat kernel. So roughly you can do something like this. Of course, one has to be careful about periodicity. Okay, so I'm going to put a constant here, P. So okay, periodicity constant. But let's not bother about this periodicity constant. Just to keep things simple, we will assume this is just 1. Okay, otherwise it would have to be 2. Let's say if you are, yes, a simple random walk. So, okay, so when you put here x equals 0, so this exponential drops out, so you get 1 over basically some constant n to the d half, the thing that you are having here. And let's say up to constants, for d equal 1, this behaves like n to the 1/2, capital N to the 1/2, right? So if you sum 1 over square root n for n from 1 to capital N, you get n to the 1/2. If you are in d equal 2, this is like log n, blows up like log n. Okay. If you are in d bigger or equal to 3, this is finite, bounded. Okay. So if you would like to tune down beta going to 0, well, the only relevant case is either dimension 1 or dimension 2. Okay. So that's where you have also kind of the Snow disorder or the disorder relevance. Okay. And dimension 3 and above is very interesting. And there's lots of very interesting problems here. I mean, the polymer model has been extremely rich. There were also, I mean, started with, yes, already in the 80s, when the physicists introduced this as interface for the Ising model. But then because of the relations with the Kardar-Parisi-Young universality, it got a life of its own, and you can view it as, you know, motion in random media. It's a very, very rich object with incredible amount of connections. So in fact, actually, I wrote, there is, of course, there is a book by Francis Comets called Random Polymer Models or Direct Polymer Model. That is Saint-Flour Notes, which I recommend to take a look if you would like to learn about the subject. And last year, I wrote a review paper with some more recent developments. The book of Francis Comets came out, I think, maybe 2017. But there have been also other developments, in particular the past 2-3 years, with the important works of Stefan Jung from, now he's in Japan. So I wrote a review about polymer models, which unfortunately it was in the memorial volume for Francis Comets. It would be nicer if this review was for a more happy event. Okay, so you can find some of the problems here in these references. Right, but okay, so coming back to our business. So in dimension 1, how would you need to tune beta so that, let's say, the variance of the first order stays bounded? Well, you would have to tune beta n equals beta hat n to the negative quarter Okay, and that was already done by Alberts, Canning, Castell, and they used this to prove that the partition function of the direct polymer model, when you do this, is what's called intermediate disorder scaling, converges to the solution of the one-dimensional stochastic heat equation. So this converges to the 1D stochastic heat equation, which is a well-defined equation, stochastic PD. In dimension 2, this computation tells you that if there is any hope to get anything, you would need to scale the temperature logarithmically as a square root of the log. And as we discussed, dimension 2 is critical. So actually, the equation doesn't make sense. So you cannot say that this will converge to the stochastic heat equation in dimension 2 because the stochastic heat equation in dimension 2 is not well defined, is not defined. And actually, this procedure is what allowed us. So we started this research program with Caravena and Sun. Yeah, or like now it has been quite a long time now. So having these limits actually gives a sense of the stochastic heat equation because we have a discretization. The direct polymer model is a discretization of the stochastic heat equation. And then having the limit, you can interpret it as what the solution of the stochastic heat equation. Only that you cannot write the stochastic heat equation, the solution explicitly. It takes different forms. While in dimension 1, it takes the form of iterated linear integrals, where you have this expression in dimension 1. You replace this by integrals, time-space integrals. You replace this by the heat kernels, and you replace this by white noise. In dimension 1, this expression makes sense. In dimension 2, it doesn't make sense. You cannot write this. So studying these limits in dimension 2, it gives you, different forms of solutions. Okay, right. So this is how one would get the guess of how to tune the temperature beta if there is any hope to get some limit. Now, of course, you can ask that, okay, beta, you guess beta by just looking at the first order of the chaos expansion. What about the rest? It turns out that this is consistent with keeping the variance of each one individual term finite. So if you put beta in this particular way, each term in the chaos expansion will remain finite. I would like actually to expand on this computation because this is quite important. So I would like now to look at the variance of the whole series under this beta n scaling. I think, so here is a multilinear polynomial. So, okay, I'm going to write the expression for the variance, and then we will try to understand this. So the expression will be summation k greater or equal to 1, beta to the 2k, summation n1 less than nk, z1, zk, in z2. And now everything will be squared. So then I'll have the product p ni minus 1 squared zi minus zi minus 1. Okay, so the claim is that this is the variance. So we can visually see this in a much simpler way, again, by the graphical representation of the chaos expansion. So how do we represent the chaos expansion? So you have here, let's say at time 0, you're at location x, and you pick k points. in the space-time domain. And then you jump between these points with transition probabilities P and I minus Ni minus 1, Zi minus Zi minus 1. So this point is, okay. So this is the weight you put on the lace, the probability to jump from one point to the other. And at each dot, you sample the noise psi and Zi. Okay, so wherever you land, you have this. So the dots represent these things. So maybe I'll even use the red color. At the last point, I don't have noise, so this is just Ny. If I would like to pin down, let me use yet another color. So this part here. So the yellow means that I don't have noise. I just pin down the walk to be there at that time. Now, so you sum over all kind of, you take a big sum over all possible locations of these dots and possible number of dots like this. Now, if you would like to compute the variance, well, by Fubini, you double. So maybe you have another set of points. If we have green, or maybe I will use pink. Okay. So it's as if you take another sum and you jump from place to place. Eventually, the two things will come together. Okay. Now you take the expectation of this with respect to the size, but because of multilinearity, right, these things need to match. Because, so what I'm saying is that they need to match and give me a diagram of this form. So okay, why is this? Because if I have an isolated red dot, when I put expected value, the expected value of this will be 0. So things will be killed. If these two dots match, here you will be having xi, let's say nz squared. And then when you hit it with the expected value, you will just be getting 1. So in any case, all in all, we get this explicit expression for the variance of the partition function. And then we would like to analyze this. So now some interesting things will appear. Okay. So let's start. Any question about this? Okay. So how I'm going to analyze, I want first to sum out the space variables in the same way I did in the case k equal 1. For simplicity, let's look at the free case. Okay, so simplicity. Point to plane, I called it. Which means I don't want to pin down the last part. Okay. Eventually, one will have also to deal with the pinned case, the point-to-point case, but the computation is more subtle. So now we have this expression, and we want to start summing the z's. So this is nk, zk, nk minus 1, zk minus 1. So I want to sum up the zk, but it's a loop that I had before. So, and then I use a Chapman-Kolmogorov. So if I sum this, it's as if I go at time twice this duration from this point back to here. Okay. So I'm going to write what this is equal to, and then we can discuss it more. So this is summation k greater than or equal to 1, beta n to the 2k, and summation n1 less than nk less or equal to n, p 2n1 at 0, p 2n 2 minus n1 at 0, p 2 nk minus 1 at 0. Okay, do we see? Because if I sum this part here, it's as if I have a loop going back, and the special location drops out. And now I sum this space. Then I use Chapman-Kolmogorov again. So this is then as if I go back. Okay, so what I used is that summation p nk minus 1 zk minus 1 squared. When you sum over all the zk's is p2 nk minus 1 going to 0. Okay, and then you will have to do the same thing with zk minus 1. So when you sum zk minus 1, you will have nk minus 1 minus nk minus 2, zk minus 1 minus zk minus 2 squared. Okay. By translation invariance, zk minus 2 is immaterial. And then use Chapman-Kolmogorov. Okay, so then I get this expression. And then at this stage, I can informally replace the transition probability kernels by hit kernels. So informally, I can say that this is almost equal Pn to the 2k summation n1 less than nk less or equal to n 1 over right. So let me just forget about the pi's and the 2's. So I'm going to have n1 times 1 over n2 minus n1 okay. So here I use the fact that p and 0, if we forget also in dimension 2, if we forget also the periodicity constants, is like 1 over 2 pi times the time. Okay, and then of course you will need to carry all the constants carefully and the 2 pi's carefully, but just not too heavy the blackboard. I'm saying, okay, let's set 2 pi equal 1. That's actually a famous saying by Littlewood, you know, from Littlewood and Hardy, from Hardy and Littlewood. Let's set 2 pi equal 1. Okay, so here I set 2 pi equal 1. Okay, and now here comes the fun part, the fun probability part. So you would like actually to say something about this convolution. Convolutions are difficult, but if you are a probabilist, that's where the fun part comes. Because convolutions is just the the densities of independent random variables. Okay. So we can write this convolution in the following, not yet, I will write this convolution in a probabilistic way. So let's set random variables Ti, which will be IID, with the density, the probability that Ti equal n is 1 over log capital N. Capital N is this, the time horizon that I'm working with, times 1 over n, if n is less or equal to capital N. Formally, this is a probability, right? Because when you sum little n, this is like log n. Of course, people can complain that this is, if I sum 1 over n from n equal to 1 to capital N, this is not exactly log n. But you can fix this problem. So let's just informally think that this is log n. Okay, we can fix this. And then recall that beta n was chosen as 1 over square root log n, beta hat. So this actually is beta hat to the 2k divided by log n. Okay, so then I have 1 over log n. So I have products 1 over log capital N, nk minus nk minus ni minus ni minus 1. Okay, I equal 1 to k. But of course, the range of all the n's is between 1 and capital N. Right? So here I have the summation between 1 and capital N. That's why I have this constraint here. And now, well, this is exactly this is exactly right. The probability that tau n plus tau k is less or equal to capital N. Okay. Because we can see this as ni minus ni minus 1 to be the density of the Ti. And then, of course, we have that the summation ni minus ni minus 1, I equal 1 to k, is equal nk, which is less or equal to n. Okay. So these are the Ti's. So you have this jump process, the Ti's. The total sum of the Ti's is less or equal to capital N. And then you would like, yeah, so next step then, now comes, so how would you like to study these sums? Well, we would like to get n going to infinity. So the question is there a scaling limit for this when you tune k somehow? Okay. And how would you approach this? Well, even though I disadvertise so much characteristic functions, you can use characteristic functions. But this is because now this is a sum of independent random variables, right? So characteristic functions are very good when you have sum of independent random variables or convolutions, but it's not good when you don't have sums. But if you have sums, that's the best way still. So maybe I will reveal part of the answer. So there is a limit theorem, and that actually gives rise to stable laws. You can see the stable law here, right? The exponent here is 1 over n. Okay, so it's a zero stable law. So the position is that if you sum s log n, log capital N, of these variables, s will be something that is free to play. Okay? And you divide by n, this will converge in distribution to some process ys. In fact, actually, this can be done at the level of a process, so s greater than 0. Okay? Which is what we call the Diekmann subordinator. Okay, so we will check this. But now let's use this to see what is asymptotic behavior here. Okay, first of all, if beta hat is strictly less than 1, if we are in the subcritical case, remember when I was looking at stochastic heat equation, the critical dimension 2, we saw a phase transition happening at beta hat equal 1. Okay, we can already see the phase transition here, right? Well, the signature of the phase transition. When beta hat is strictly less than 1, this series is geometrically convergent. Because the probability is less than 1, you sum geometric series with a parameter beta hat square, which is less than 1. So the variance stays bounded. Interesting things happen when you look at the case, at the critical case, when beta hat is not 1, is not strictly less than 1, but is 1. In fact, actually, you can allow for the critical window. I don't know if you remember this theta from my Tuesday talk. Okay. So then, in this case, we have 1 plus theta over log n to the k times the probability that the sum of the jumps is less or equal to n. Okay. And now the claim here is that I see something interesting happening when k is of order s log n. So now you change kind of you sum k over log n, which is going to be the s times log n. Okay. So okay, so then we change variables. Let's change variables. 1 plus theta over log n, s log n. Now, do I want to do it this way? No, maybe let me not do it this way yet. So I have k over log n because I want to show. Actually, can you see here? I say I want to show, but can you see here? Or is it too dark? Okay. So I multiply by log n because this is going to be the natural scale. The probability T1 plus T k over log n times log n less or equal to n, but I can divide by n and say that the probability that this is less or equal to 1. Again, I divide by n because this will be my limit theorem. So I want to bring everything at the form where I have a limit theorem. And now, well, now what do we do here? So we want to sum over k. but K is scaled by log n. So this is now Riemann summation, which is, we learn Lebesgue integration and measure theory. Even though this lecture is recorded, I will not be scared to say that actually I don't like measure theory because you detach yourself from the practical issues like Riemann. Okay, Riemann, we forget about Riemann. We go to the abstract, but we shouldn't forget about Riemann. So here we want to do a Riemann sum approximation. So we would need, because K is scaled by log n, the Riemann factor will be 1 over log n. So we put this, and then we also put it reversely so that the expression doesn't change. Now, by that proposition, this thing will converge to the probability. So if, let's say, K over log n converges to some continuous S, then by that claim, this probability will converge to the probability that the Dieckmann subordinator is less or equal to 1. Okay. Now, this 1 plus theta over log n is going to be approximately e to the theta over log n times s if k over log n converges to s, right? Because 1 plus x is almost equal to x if e to the x if x is small. And of course, the log n's cancels. And then this is going to become the Riemann sum integration. So this is going just to become the integral. Okay, and of course I shouldn't, this log n didn't do anything, so it's not, it remains. So all in all, the variance of the direct polymer model at the intermediate is of the scaling beta over log n when beta hat over log n, when beta hat is equal to 1, actually it's in this critical window around 1, will converge to, will be approximate log n times this thing here So elementary, but a very, it shows actually the power of probability, right? You have a convolution, you express it as sums of independent random variables. If you can express something as sums of independent random variables, you have the power of characteristic functions. You compute some characteristic functions, which we will do it after the break. And then you try to see what is the scalings, what are the natural scalings. You put the natural scalings in, then you turn everything into an elementary Riemann sum approximation, but you get very precise asymptotics, which are extremely important also for the business that we are interested in. Okay, I think it's probably a good time to have a break now, because I think this clock is 5 minutes late, and if we finish at 3 o'clock, the cakes will also finish, because people will go ahead of us. And then when we come back, I'll do this characteristic function simple computation just to complete the story. And then I will have a little discussion about this and the Dieckmann function. And then I'll pass to higher moments and collisions of random walks. And soon we'll be over. Yes, so, okay. And then I would like to describe a bit the Lindeberg for the stochastic equation, the stochastic flow. I'll see if I don't have time to do both our approach and size approach, then I will do just size approach. Yes. Okay. So yeah, we'll resume after the break. Okay. So yes. Okay. So we are doing variance computations for in case somebody was not here in the last hour, and then we compute the variance of the polymer partition function, and then we which can be explicitly written as the top line convolution, and then we re-express the convolution as a probability, and then we run a kind of Riemann sum approximation to show that eventually the variance of the direct polymer model at the critical temperature and in dimension 2 blows up logarithmically and has this very important prefactor, which is very crucial if you remember the scaling argument I had in my talk on Tuesday about the invariance of the polymer, the self-similarity. Well, this is what gives basically the, okay, lots of information capsules here. So to complete this argument, we needed to check that this proposition, that the sum of this family of IID random variables with distribution written up there, the probability that t equals little n is 1 over little n if n is between 0 and capital N divided by log n. And so let's do it. So you compute the characteristic function. And then you have a sum of independent random variables. So this is the product of all how many of these you have as log n. And then we just simply write the expectation as by its definition. So lambda n over log capital N times the probability that tau takes the value, that t takes the value little n, which is 1 over n, if n is between 1 and capital N, and with the normalization 1 over log capital N. Okay. And all this is to the power s log n. Okay. And what we do here, because we would like to have things in the exponents, so we would like to express like something like 1 plus x, and then 1 plus x to be like e to the x. So we subtract 1 from here. Subtract 1. And then we add the 1. But if you add the 1, you get 1 over n for n equal 1 to capital N divided by log n, which is equal to 1. So then this will give you a 1 outside. Sorry, over n, yes. Yeah, thank you. Okay. And well, again, Riemann sum. So Riemann sum, we would divide here by n. and then we will get the Riemann sum factor. Maybe I'll not do it the Riemann sum yet. So this is of course the 1 over the log n. So asymptotically, this is 1 plus something small. So this is like e to the something small. So 1 over log n summation n equal 1 to capital N e to the lambda little n over capital N minus 1 over n multiplied by s log n. Then if we multiply by s log n, it will cancel this log n. So we'll be having here s. And now we want to take the large n limit. So now we do a Riemann sum integration. So we divide and multiply by n. So that we have the Riemann sum factor. So here, little n is already scaled by capital N. So I scale everything by capital N. And this is just then, just by Riemann sum integration, as n goes to infinity, this will converge to the exponential as the integral between 0 and 1 e to the lambda t minus 1 dt, or maybe x, I put x over x. Okay, so that's the way you can check that you have a limit when you look at the sum, when you scale k here by like s log n. That's the natural scale where you see something when k is s log n. And this is a Levy representation, right? Of course, you have a sum of independent random variables ID. The limit has to be a stable law. So you get a stable law with Levy measure nu dx equals 1 between 0 and 1 over x dx, right? So between 0 and 1, okay, because the integral runs between 0 and 1, it doesn't run on the whole real line. This, of course, this integral is finite because for x small, this is like x, cancels this x. So this is the Levy measure, the jump process of the Levy measure. And this is a subordinator. Typically, a stable subordinator has a Levy measure, which is a dx, x to the 1 plus alpha. I think 0 to 1. Okay. This is a typical Levy subordinator when you have limits of sum of IIDs with heavy tails. Okay. And then, of course, you don't look at S log n, but you look at 10 of them, right? And you scale, you don't scale by n, you scale by n to the 1 over alpha. Okay, so the Levy, if you have heavy tails, this is the alpha. The alpha is the tail, the jump distribution. Okay, so here the tail is 1 over n. Okay, so basically you hit here the alpha equals 0 case, but then you also truncate at 1, because if you let this being infinity, then this wouldn't be integrable at infinity. Okay, while here for any alpha positive, this is integrable at infinity. So this has a feeling of a zero stable Levy process, so it's like zero stable. Truncated zero stable Levy. And that's what the name we gave at the beginning. So in fact, actually, we could compute, actually I should say that one of my collaborators, who is very good at these Levy things, was able to compute the density with a very nice argument that, so this has actually some invariance. So if you condition, if you look at the sums T1 and T2 and so on, and you look at the distribution conditioned that everything is less than some number T, then actually everything scales, because when you condition, you scale everything by T. If you divide by, here you have some invariance in T. Okay, it doesn't change if you scale by T. Okay, so if you scale by T, you have some invariance, and using this invariance and the infinite divisibility, you can actually compute the density of this object. And the density is let's see, right. Let me see if I forget something. Sorry, just a minute. Yes. Yes. Okay. When T is less than 1, less or equal to 1, when T is bigger than 1, the density takes a bit different form. Again, we can write the density by renewal argument, but let's not worry about this. But this is actually, when we called it zero stable. And then the day after we posted the paper, somebody called us and said, okay, this density is called Dickmann function. It's very important in number theory, in analytic number theory. So then we call this Dickmann subordinator. And actually, I would like to write some things about the Dickmann function. So the Dickmann function, it takes this form between 0 and 1. It takes a bit, it has a delayed recursive equation for T bigger than 1, but let me not write it. But in number theory, so there is this object called Dickmann function. Okay, so this we call this Fs of T. Okay, so if you put S equal 1 and you put here 1 over T, this is actually the asymptotic probability that the largest prime factor of a number between 1 and little n is less or equal to n to the t. So as n goes to infinity. Okay, you pick a number at random between 1 and t, and you ask what's the probability that the largest prime factor is less than n to the t. So Dickmann computed this and found this expression where, yes, this function f that we also recover appears. And this is bread and butter of number theories. This is they use it the same way we use Borel-Cantelli, as I understand. And also, Dickmann function appears in random permutations. So actually, for a reference for the number theorem is a book. The classical book is the book of Tenenbaum. Okay, and in random permutations, there is a nice book by Aratia. Barbour and Tavares. And they found that this function here, rho 1 over t, is the asymptotic probability of the largest cycle in a permutation in Sn to be less than n times t. Okay. So, you know, when I teach graduate probability, the examination has two parts. The one is an oral examination, and another is some students have to choose a project among a list of projects, and then they have to write an essay and do a presentation. So the projects is basically 3 additional ways to prove central limit theorems. So central limit theorem for martingales and for Markov chains, and then the fourth moment theorems, and then the dependency graphs. But then I also have a fourth project because I want to get I have some students in analytic number theory and probabilistic number theory taking the class. I want to learn from them. So I have a project on Dickmann function. And actually, they tell me many interesting things. There is a Stein method for Dickmann function, actually. It's very interesting. So I think this may be actually interesting projects to look at. And all this kind of how, you know, how even actually the derivation of Dickmann is very interesting. It has a kind of structural probabilistic with a prime factorization, and then there is not so much surprise that these are connected with cycles of permutations. And in any case, in both cases, what's at the core, there is some logarithmic structure, both here and here, and that's why actually in our case on top also the Dickmann function appears, because of all these logarithms that underlie the object that we look at. So somehow, if you have some object, some combinatorial probability object that has some logarithmic structure, maybe at some point Dickmann is going to show up for some magic reason. Okay, so these are the variance computations. Now, I would like actually to go from the variance to the covariance. Because I was, you know, advertising a lot before, so that you know, if you want to have a limit theorem, you need to somehow make sure that the fluctuations stay of order 1. So then you compute the variance, and the variance should be kind of finite. But here we don't see anymore, but it was there, that the variance blows up logarithmically. Yeah, we see it here. The variance blows up logarithmically. What's going on there? Okay, so this is actually a reason why this indication of the fact that the stochastic heat flow is not a function. That's why it has these spikes that I was showing. If you look at one point, it will kind of maybe typically will be 0, but it will have very huge variance. So that's why at some point you will get something very big. So this is called intermittence. Okay. But how can we construct these objects? So the point is that if we test the polymer partition, let's say starting at location X, and we test it against some test function. Okay. So this is the Riemann sum factor. We are in dimension 2. Okay, so the Riemann sum factor is the volume is 1 over the square here, the scaling. So the claim is that at beta hat equal 1, so this is critical, let's call it critical. This will converge in distribution, and the object that will converge to is SHF theta x phi of x dx on R2. Okay, so still we can have some convergence. And why we still have some convergence even though the variance of this object blows up? Well, because correlations are still kind of okay. So for example, if you would like to compute the variance of this, so maybe if I would, the variance of this. So how this would go about? Well, we can center it here, subtract 1, okay? And then we compute the second moment of this object. So if we square it, then we'll have 2 summations, if we double the summations. So then it will be 1 over, let's say, n squared, summation, x and y, the expectation, or maybe the expectation of the covariance. Okay. And now we need to understand then the claim is that, well, this covariance will still be okay, it will not blow up as long as we look at points x and y, which are square root n apart. And what's a heuristic while that doesn't blow up? So, well, let's take 2 points x and y, which are distance square root n apart. Then you can have again the same similar picture that I have. So you start to chaos expansions, okay? You expand this in terms of chaos. So you would have 1. But then when you take the expectation, the noise is here, they would need to match. So the picture will be that you have 2 polymers, starting one at location x, another at location y, and they go meet at some point. And then they will start meeting. Okay, they start colliding. These are the collision times that I was talking about. Now, there is a result of Uchiyama. It was published in EJP, I think maybe 2011. Or by the way, in last December, we wrote a review with Francesco and Trionfeng called the Critical Stochastic Heat Flow and the Related Models. So yeah, most of these things, except the first lecture, can be found there, and also some things about polymers. So if you are interested to look at more details. But okay, let's go back to our business. So there is a result of Uchiyama, which says that if you start 2 random walks at distance square root n, and you ask what's the probability that they will meet before time n, this decays like 1 over log n. But then once they meet, so in other words, the probability of this part, so the probability that this happens is 1 over log n. But once they meet, they start picking the variance. Okay, because they start from the same point, like here, both of them we consider starting at 0. Okay, and they start colliding, and then this blows up like log n. So the blow up that you have at the critical case is actually compensated by the covariance blow up, the covariance decay. And that's overall this stage of order 1. And that's why eventually you can have a limit. So this actually shows tightness. The difficulty actually to show that there is a unique limit. Okay, so let me elaborate a bit more on the correlation structure. Well, I would like to have this picture and then combine it with this one. So what do we get? If we would like to get, if we would like to, this is n. So if we squeeze everything time by n and space by square root n, okay, what kind of a scaling limit we will be having? So these parts actually, we can use the local limit theorem, saying that this probability going from here to that point will be approximately like the heat kernel. Okay, so then we have, let's say in the continuum, x and y, we have, let's say this is a time s, and then we have gs, we call this z minus x, so the heat kernel, and this will be weighted by another heat kernel gs z minus y. And after that, I'll have all the collisions. So over here now, I'm going to have this. Okay. By the way, we call this we call this g theta s. So right, and then it goes all the way with collisions up to time 1. So this will be g theta okay, let's call it g theta s. So overall, the limiting covariance is going to be equal to the, okay. So now this will not depend on space, right? This doesn't depend on space. So when now you integrate over z's, okay, so this is going to be integral over z over all possible z's that the two random walks or the two continuous Brownian motions meet, z minus x times g s z minus y times g theta of s. And then, of course, we have to integrate over the time they meet. Time can be anywhere between 0 and 1. And actually, this should not be g theta 1 minus s. It's better to write. Okay, because this counts the duration, which is 1 minus s. Okay. So now I can do the integration with respect to z, because I can just use Chapman-Kolmogorov. So as if we go from x at time s to z, and then from z back to y. This is just then g 2s x minus y, and then I have the g theta 1 minus s, and then I integrate over ds. Okay, you integrate between 0 and 1. So this will be the correlation function of the stochastic heat flow. And the point I want to make is that, well, how does the correlation function behave when x and y are converge. Okay, so if x and y, they become very close to each other, of course they will coalesce very quickly, right? So then this will be basically, I mean, this will kind of factorize out. I mean, this will become approximately g theta of 1 when s is small. Okay, so then this will become approximately but this is the Green's functions of two-dimensional Brownian motion. Okay, one has to be careful when they discuss about Green's function of two-dimensional Brownian motion, because typically the Green's function from 0 to infinity, but this doesn't exist. Here is from 0 to 1. Okay, but for all purposes of matter, when x and y go close to each other, it doesn't matter so much whether this is 0 to 1 or 0 to something much bigger. The point is that this will behave, it will have a logarithmic blow up. Okay. The Green's function, if you look at the Green's function, the simplest thing to look is to compute is the Green's function in a bounded domain, in a bounded circle. This you can compute it precisely. And the Green's function in the solution of the Laplace u equals delta 0 is log 1 over r, maybe with a constant 1 over pi in front, but we have set pi equal to 1 and 2 pi equal to 1. Okay. So this brings connections between all these very important studies that have been done in two-dimensional statistical mechanics and are related to Gaussian free fields, which is log correlated fields. Only that the object that we are looking at, the stochastic flow, is not a Gaussian. Okay, though it's log correlated. But then you can start all questions like, what are the relations between the stochastic flow and, let's say, Gaussian free field, or the exponential of a Gaussian free field? And I think there are lots of interesting things waiting to be explored here. For example, actually, maybe let me write what is a Gaussian free field. So let's say you have a domain. You can think of it as a kind of, in the case of a discrete object, if you would like, you can think of a grid in a domain. And then the Gaussian free field is a Gaussian process, a Gaussian field on this domain omega, whose covariance, so it's a mean zero Gaussian field, whose covariance is the Green's function on this domain. Okay. You can think the Green's function in a finite domain as the integral, let's say, of the heat kernel for, the random walk run up to the heating time of the domain. Okay. But the point is that when z and z prime approach each other, this blows up logarithmically. Again, there is a constant 1 over pi, because when you zoom in, you don't see the shape, really. Just if you look at the unit disk. Okay. So this is the Gaussian free field, a very important topic. There are lots of notes, lecture notes written. While I was here, I looked at some notes of Wendell and Werner. I think they're very nice notes because also they make more connections with statistical mechanics and spanning trees. There's some beautiful connections. Like if you compute an integral of a Gaussian free field, this gives you the number of spanning trees. So there are all these very beautiful combinatorial connections that I think, yeah. Actually, I was planning to read this while I was here, but I also spent some time preparing my lecture, so I didn't read it. But I think I would recommend these notes. Now, one point is that the Gaussian free field, again, if you see it has some spikes, and people studied a lot what is the typical maximum. So if you look at a discrete Gaussian free field, let's call omega n the grid. You think of the grid being size 1 over n. You scale it by 1 over n. So what are the maxima? So these have been studied to death. I think maybe there are thousands of papers studying the maxima. There are interesting relations with branching Brownian motions. We're discussing, that was also the motivation maybe to have this discussion here today about the maxima. But I think maybe this is a preview to the future discussion. So there are some universal constants here. So if here, if you have n sides, so this will be some constant C1, which is rather universal. It can be computed for the Gaussian free field, but for many other local related fields or branching random walks is the same constant, log n. Plus there is another constant, typically 3/4, depending on the parameters, but 3/4 is the core, log n, plus something random. And the random in general is very, very difficult to compute. There are some conjectures, the Fyodorov-Keating conjectures. Okay. Sometimes it's Gumbel, sometimes there's a conjecture that this is a mixture of Gumbel. There are some formulas about the random part that is a derivative of a Gaussian multiplicative chaos. Okay, this Gaussian multiplicative chaos will bring maybe to the last part of my talks. So in any case, you can also ask similar questions. So you have the stochastic heat flow. What is the typical maximum of the stochastic heat flow? Let's say if you look at the log, or if you look at the Zn at x, if you look at the maximum, what is the typical behavior? Well, actually, this line of research was started recently by Zeytouni and Kosko, because Zeytouni was, for the past decade, was working on the maxima of local related fields. And they have started looking at the subcritical case. The subcritical case is easier for many points of views, but also still very, very rich. And recently, with Kosko and Nakashima, they were able to identify the first constant here, which is actually non-standard from the point of view of maxima of local related fields. And then one could guess that the second term should be log n, but Zeytouni conjectures that maybe here there is anomalous scaling, maybe 1/3. Again, because of the particular kind of branching structure that there is in the stochastic flow. So, okay, questions. So these are kind of big questions. I mean, these questions can also be studied in the subcritical case. And in fact, actually, the only thing that has been done is this term in the subcritical case. Right. Okay, so I would like now to, okay, we said that the stochastic flow is a local related field, but it's not Gaussian. Actually, you can easily see that it's not Gaussian because the partition function for whom we take the limit and we obtain the stochastic flow is a non-negative object. So the limit is non-negative, but the Gaussian is positive and negative. So this automatically excludes that the stochastic flow is a Gaussian. But then you can ask, is it the exponential of Gaussian? So is it a Gaussian multiplicative chaos, often called GMC? So this lies very much in lots of structure, lots of the things that have been done in two-dimensional geometries, random geometries, Liouville quantum gravity, and so on. So what is a Gaussian multiplicative chaos? So let's say we have a Gaussian free field, a local related Gaussian, let's say on some domain. And the GMC is formally written as the exponential of gamma, the Gaussian, minus its quadratic variation, or let's say minus its square. And this is supposed to be a measure. So it's supposed to be a random measure. So the GMC on a set A is, let's say, a subset of the set omega, where the Gaussian free field is defined. Is defined in this way. So you integrate the exponential of the Gaussian. So this first was introduced. This concept of Gaussian multiplicative chaos was introduced by Kahan when they want to model turbulence. That was in the 70s. But then in mathematical physics and quantum gravity, there are some integrals of this sort. So that's why this became so popular. And right, this is very ill-defined. Doesn't make sense, right? Because precisely X is a distribution. Is a local related field, which means that when X and Y go together, it blows up logarithmically. So the variance blows up logarithmically, which already makes this not well defined. This is infinity. But then again, you have the issue of having a nonlinear function of a distribution. How do you define a nonlinear function of a distribution? So typically what people do is they smooth out the field. So you can take you can convolve this with a kind of a nice test function, and then they can study that as epsilon goes to 0, this object will have a limit and will also have phase transitions depending on gamma. And the phase transition is kind of similar to what we see in the stochastic flow. So there is, if you are in dimension D, so the critical gamma is, if I remember well, square root 2D. Okay. So for gamma less than square root 2D, there is a non-trivial, there is a limit. When you hit a critical value, gamma equals square root D, then this becomes trivial, it becomes 0. But if you look in the pixels, it will be very zero and they will have spikes. Okay. So this is often called the critical multiplicative chaos. So, okay, so we see some similarities. So in the stochastic flow, we see a phase transition in the beta hat. So maybe the beta hat is related to the gamma. And maybe actually the stochastic heat flow that we get, because of the similarities of phase transition, log correlations, and so on, maybe it's a Gaussian multiplicative chaos. But actually, we're able to exclude that this is the case. So the stochastic heat flow is not a Gaussian multiplicative chaos. And one way, the way actually we approach this is actually by comparing the moments. So in fact, we look at a set, at a ball, let's say B, and the volume of the stochastic flow on the ball B on some power P. And then we let the ball shrink to 0. And then what we were able to show is that in the limit, if you compare this with the corresponding GMC volume, this is strictly bigger than 1 in the limit as delta goes to 0. Okay, don't think I'll have much time to say about much about this, but I would like to give the main idea. So this brings us actually maybe to another huge, another very big chapter, which is about higher moments. So what will be, we discussed what is the second moment of the partition function of the polymer, but what about the pith moment? Or maybe the mixed pith moment. So you start at different locations, x1, x to the p. So what is a mixed pith moment? Okay. And now you can have, so you have x1 here, x2 here, x3, x4, and so on and so on. How can we diagrammatically represent the mixed moment of the polymer partition function? Well, again, we look at the chaos expansion. So here we'll be having 4 paths sampling. So every dot here is a noise, and the noise is mean 0. So when I take the expectation, this expectation here, I have to match all the noises. Otherwise, if some noise has remained unmatched, when it's hit by the expectation, we'll give 0 and we'll kill everything. So right, in this, when p equal 2, I had this type of diagram. Now, in higher p, the diagram will be as follows. So you'll pick 2 of the walks, and these walks will start meeting, colliding. Okay, and then they will split, and one of the walk will go meet with another one, and then start colliding. And then maybe this walk now will go meet this one, start colliding, and then these 2 will start meeting, and then maybe later on these 2 will start meeting. So you have this complicated diagram of collisions. On the other hand, if you would like to compute the mixed moments of Gaussian multiplicative chaos, you can use the Gaussianity. Okay. So this will be, so this is just a Gaussian computation. Right? This is nothing more than computing the Laplace transform of a multivariate Gaussian, which is e to the lambda squared divided by 2. No, actually, e lambda, the correlation matrix So if you do this, then you have that this is equal to the product E to the K Zi minus Zj, I less than J. Okay. So this is the correlation function of the Gaussian free field. So one thing that maybe, I mean, when you see the picture, even though you need to do something to justify, but you see that if it was a Gaussian multiplicative chaos, you would have a factorization, meaning that here the collisions will become independent. Right? So if it was a Gaussian multiplicative chaos, then we'll be having kind of the product of the pairwise collisions. My notation is not good. Let's say the total collision time by time n between walks I and j. But this diagram is not, that doesn't look to factorize. Okay. So this diagram at the critical temperature doesn't factorize. Actually, it's interesting because if you were in the subcritical case, this diagram factorizes. So below the critical case, you have some Gaussian structure. And that's what also Kosko and Zeytouni and Nakashima, they used a lot to get the maximum, to make some comparisons with the Gaussian fields. Yeah. Okay. Okay, so I know that these are very sketchy, but maybe I now would like to give a bit of a bigger, broader picture, and with the hope that it will trigger your desire to learn more. Maybe I would like to close with contributions, let's say, from the local community. So I would like to close with Chai's characterization of the stochastic flow. This is a very beautiful paper. So it's called heat flow by moments. Heat flows by moments. And actually, it is a broader framework grounded really on the Lindeberg principle. So that's why I want to bring this, close the cycle. So he gave a characterization. So the stochastic heat flow okay, so maybe if, let's say, Z theta is a measured valued, is a continuous measured valued flow, let's say, although we haven't really measured valued process. Which satisfies a kind of a Chapman-Kolmogorov equation. So ZTU is equal to ZSU. This is clear for the partition function because of the Markov property. However, when you pass to the limit, the stochastic flow, this doesn't make sense because this formally is very ill-defined because these are measures. So how do you stitch together the measures? Okay, so you need to have a kind of a particular convolution, and this was actually defined by Clark and Meehan for the stochastic flow. The last one, the third condition that you have is that you have independence. So the increment between S and T is independent to the increment between T and U. And suppose that the first 4 moments of Z agree with that of the SHF. Okay. So the first 4 moments are given by such kind of diagrams. Then this process has to be the stochastic heat flow. But this is actually a larger framework. So he also works as a warm-up, an example where basically some sort of an Einstein-Lindeberg process. The point is that here you can compute all moments of the stochastic heat flow. But the moments, there is a conjecture that they grow too fast. They grow like e to the p. So they cannot determine, the moments cannot grow too fast to determine the distribution. However, just 4 moments is enough if you combine with these kind of independent increments and the kind of a Chapman-Kolmogorov. And why is this? Well, I really can give you the argument in 5 minutes. Well, let's suppose that we have two flows, let's say between 0 and 1, and we want to compare with the z tilde between 0 and 1. If we would like to identify the distribution, we just need to have that the expected value of the two, the difference of the expected values of the twos is equal to 0. And that's where the Lindeberg comes. So here you have 0 and 1. And we can telescope this. So we can break this into many little strips. So Ti, okay, that the mass is going to go to 0. And then minus so let's call actually the one, let's call it white, and the other, let's call it maybe red. So what do? You go up to the ith point with the white flow, and then you continue with the red flow. Continuing uses this Chapman-Kolmogorov, the generalized Chapman-Kolmogorov in the sense of measures. Or you can compare it. You go up to T minus 1 with the white flow, and from Ti minus 1 to 1 with the red flow. Okay. And then, of course, you test this against some function f. So I equal 1 to whatever. I need my yellow chalk. Anyone sees a yellow chalk here? Okay. So there is a discrepancy only. I think I would like here to go up to here with white. Okay. There is only discrepancy here. Because before this strip, both of them use white. After that, both of them use red. There is only one part. This is exactly what we did in lecture 1, right? And then you do a Taylor expansion around this discrepancy. And then you use the matching first two moments. Actually, I think his condition that you need to have match first 4 moments is not necessary. So you just need to have matching 2 moments. And you need also to have some control on the 4th moment, that the 4th moment is finite. Okay. Of course, if you know that the 4th moment of the one flow agrees with the 4th moment of the stochastic flow, then you have finiteness because we know that it's finite. But I think his result, yeah. Then you do the Taylor expansion exactly the way we did it. Okay, but instead of having x1 plus x2, you have to do it a bit more carefully because now you need to stitch the measures. And when you do the Taylor expansion, that's where you will use the independence, which is also what we used for the sum of independent, identically distributed random variables. So we need the independence too. And then, of course, there are questions of zero-a. If you don't have independence, then okay, that's I don't think the theory, the Lindeberg theory, has been developed, but it's of course very interesting. So now, if you start taking the mesh to 0, Taylor expansion, the influence of its, because of the having 4th moments, the influence of its small strip that you have the discrepancy is small. And then this will go to 0 as the mesh goes to 0. Okay, so then these two things have to be the same. And I think this is perfect time to stop, right? It's really on the dot. Well, thanks very much for staying with me all this long period. I enjoyed interacting with all of you, and I'm looking forward to further interactions. Thank you.